Okay, let us go back to continue the second part of today's class. Okay, let us see what is TC. Okay, T times C. Okay, a scalar times a set. Its meaning is this. Okay, it is easy. It is equal to TZ, and where Z is in where T Z is in the original set C. Okay, like this. Okay, it should be italic. Okay, italic. Oh, sorry. Okay, and okay, it is here in. Oh, sorry. Okay, C. Okay, like this. Okay, next. Okay, what does this mean? Okay, this means that. Okay, let me use this again. Okay, it means that it's TZ. Okay, and TZ is in C. Okay, and the absolute value of TZ, okay, is equal to the absolute value of T times the absolute value of Z. Okay, which is smaller than or equal to the absolute value of T. Okay. Okay, this is because in the set C, the absolute value of Z is smaller than 1. Okay, so it should be italic. Okay, TZ. And T should also be italic. And this Z should be italic. And TZ should be italic. And T should be italic. This Z should be italic. And this is smaller than or equal to okay, this operator, and it is smaller than T. Okay, so it is equal to, okay, let me use this again. Okay, it is equal to Y. Okay, where Y and T. Okay, stat italic Y and italic T is in. Oh, sorry. It should be the set of all the complex number. Okay. So here T is in C, and sorry. Okay. And the absolute value of Y. Okay, let me copy it. Okay, Y, okay, is smaller than or equal to T. Okay, let me align at the equality sign. Okay, good. And this should be equation 2. Okay, good, perfect. Okay, where, oh, sorry, small w, where we let y is equal to tz. You can see that tz becomes y, and tz becomes y, so we do not need a z, so we delete z here and replace by y, and tz is equal to y. It is the absolute value of y is smaller than or equal to the absolute value of t. The graph of tc is as follows. Let me draw another graph here. Let us see here. Sorry. This O should be placed here. Should be here. Good. As follows. So let me draw the axis again. Like this. And here is the what happened? I know this is an arrow. So let me rotate it. Rotate it, and let me pull it here and here. And let me shrink it into a arrow, like this. But I only need one line, not two lines. So let me see. So this is not what I want. Sorry. I am not familiar with the graph function in Microsoft Word. So let me draw a line here. What's happened? Draw a line. Draw a line. Good. Draw a line. Draw an arrow here. And let me draw a disk. Draw a disk here. Like this. Good. Delete this point. So here is the real part. Real part. Yes, real part. So no fill, no frame. Good. So here is the real part, and this is the imaginary part. I am here. So next I need to place origin here. So this is the origin. Here capital O. Equation. This is the origin, and please note that it is the absolute value of y is smaller than or equal to the absolute value of t. So the radius of this disk should be the absolute value of t. Okay, let me copy and paste here. Okay, good. Okay, and here is another t. Okay, another t here. Okay, and here is the minus t. Oh, okay, minus t. Okay, here. And here is also the minus, minus absolute value of t here. Okay, so this disk is called the TC. Okay, let me copy a block box here and write TC here. Okay, so this is the set TC. Okay, and where is the x? Okay, because the absolute value of t is greater than r, and r is equal to the absolute value of x. So we can know that, okay, x must in this disk. Okay, so let draw this. Okay, so this is the x. Okay. Okay, this is the x. Okay, and the distance between the point x and the origin is equal to, okay, r. Okay, and okay, I think this graph tool is not convenient to use for me, and let me, okay, so it is equal to r, and is equal to, equal to the absolute value of x. Okay. Okay, so x should be italic and r should be italic too. Okay, so I think I need to use another color, okay, to draw this point. Okay, I think this. Oh, okay, draw another. Okay, I use the red color to draw this point. Okay, so you can see that, okay, because r is smaller than the absolute value of t, so x is in this disk, so x is in TC. Okay, so so let me, okay, input. Okay, let me input. So I need to, first I need to choose this all. Okay, to choose this. Okay, real part. Okay, and the x-axis. The y-axis is an imaginary part, and this one, this one, this one, this one, this one, x. Okay, and this one, and the disk, and this one, and this one, and this one. okay, and make them into a group. Okay, okay, like this, good. And I need to set this, okay, 文绕图上及下, okay, good. So, and I need to move this text here. Oh, sorry. I need to move this this sentence. Okay, here. So next, I can input, okay, some text here. Oh, it is very difficult for me. Oh, therefore, okay, X is in, okay, TC. Oh, sorry, TC. For all, okay, T is in C. Okay, here C is the complex number set. Okay, so T is in C. Okay, which satisfying, okay, this equation. Okay, the absolute value of T is greater than R, and R is equal to the absolute value of X. Okay, so it completes the solution. Okay, oh, delete it. Okay, so do you have any questions? Okay, I forget, you cannot answer me now. Okay, so please let me save this file. Okay, page 47, example 1. Okay, and Blackboard, wireless communication. Okay. Okay, so let us go back to the handout. Okay, so we have given an example to explain what is the meaning of this sentence. I think you should be more clear now. Okay, the set C can be scaled out by any large value to absorb every point in the space. Okay, what does this mean? Okay, let us go back to the example. Okay, this is the set C, the unit disk. So when we times C by a scalar T, okay, we enlarge this circle. Okay, so no matter where X is, okay, as long as we times a large enough T, okay, the meaning of large enough is the absolute value of T is large enough. Okay, then the disk will contain the point X. Okay, it is the meaning that absorb every point in the space. Okay, so when the set C get larger and larger, okay, it will equal to the total complex number plane. Okay. Okay, next, let us see in any topological vector space. Okay, we will introduce what is a topological vector space later. Okay, which is abbreviated TVS. Okay, here TVS. Okay, every neighborhood of the origin is absorbent. Okay. 6. Absolutely convex or a disk. Okay, what does this mean? Okay, it means that a subset C in X, okay, where X is a vector space over K, K is a subfield of the complex numbers. normally C itself or R. Okay, normally the set of all complex numbers itself or the set of all real numbers. Okay, C in X is called absolutely convex or a disk if it is both balanced and convex. Okay, do you remember what is balanced? Okay, let us go to point 3. Okay, balanced. Okay, again, a subset C in X, okay, where X is a vector space over K, a subfield of the complex numbers, normally C itself or R, is called balanced if for all X in C and scalars S, if the absolute value of S is smaller than or equal to 1, then S times X is in C. Okay, both balanced and convex. Okay, and do you remember what is the meaning of convex? Okay, let us review it. Okay, again, a subset C in X is called 1 convex if for all xy in C and 0 is smaller than or equal to t, and t is smaller than or equal to 1. T times x plus 1 minus t times y is in C. In other words, C contains all line segments between points in C. Okay, let us go back to the convex. Okay, this is equivalent to it being closed under linear combinations whose coefficients absolutely sum to smaller than or equal to 1. Okay, such a set is absorbent if it spans all of X. Okay, do you remember what is the meaning of span? I believe that you have already learned it when you take the course linear algebra. Okay, if you forget it, please review the textbook of the course linear algebra. Okay, so a TVS, TVS means topological vector space, is called locally convex if the origin has a neighborhood basis. Okay, we will introduce what is a neighborhood basis. That is a local base consisting of convex sets. In fact, every locally convex TVS has a neighborhood basis of the origin consisting of absolutely convex sets. Okay, we have introduced it earlier. Okay, about several minutes ago. Okay, that is disks, where this neighborhood basis can further be chosen to also consist entirely of open sets or entirely of closed sets. Okay, we have introduced what are open sets and closed sets. If you forget, please review the handout before. Okay, every TVS has a neighborhood basis at the origin consisting of balanced sets. Okay, we have just reviewed what is a balanced set. But only a locally convex TVS has a neighborhood basis at the origin consisting of sets that are both balanced and convex. Okay, it is possible for a TVS to have some neighborhoods of the origin that are convex and yet not be locally convex. Okay. It is 25 minutes. Let us take a break.